This is a tutorial on geometric sequences. A geometric sequence is just a sequence of numbers where each term is the previous term multiplied by some number. And every term in that sequence is always just the previous term multiplied by the same number. An example of this would be our first sequence here, 3, 9, 27, and 81. Now in geometric sequences we're using multiplication. So to go from 3, our first term, to our second term 9, by multiplication, we would have to take 3 and multiply it by 3. And that would get us 9. Now if we take 9 and we want to go to 27, we would have to take 9 and we'd also have to multiply 9 by 3, and we would get our third term, 27. Now if we take this third term and we multiply it by 3, we get 81, our fourth term. Now because each term is increasing by being multiplied by the same number, in this case 3, that means that this term here is indeed a geometric sequence. Now let's look at our second sequence here. We have 2, 6, 24, and 96. Well, to go from 2 to 6 through multiplication, we would have to take 2, our first term, and multiply it by 3 again. And that would get us 6. Now to go from 6 to 24, our third term, we would have to take 6 and we would have to multiply it by 4. So our third term would be 24, and if we multiply our third term by some number to get 96, that number also has to be 4, because 24 times 4 is 96. Now notice that this sequence, these numbers are not being multiplied by the same number each time. So this sequence here is not a geometric sequence, because first we multiply by 3, but then we multiply by 4. And for it to be a geometric sequence, this has to be the same number each time. Now when we have a geometric sequence, we can write a formula for that sequence as either a recursive formula or an explicit formula. And if it is a geometric sequence, then there's a standard form for both the recursive and the explicit formula. Now here we're back at our original sequence, 3, 9, 27, and 81. Again, each of these numbers is the previous term being multiplied by 3. So first let's look at our recursive formula. Here we have a to the n, or the nth term, or some term in our sequence, that's always equal to the previous term, n minus 1 term, times r. R is what's called the common ratio. The common ratio is just the number that you keep multiplying each successive term by. So in this case, our common ratio is 3. So a recursive formula for our geometric sequence is just every term is the previous term multiplied by the common ratio. And the recursive formula for this geometric sequence would be that our nth term is always the previous term, or the n minus 1 term, times our common ratio, which in this case is 3. If you want to simplify this a little bit, our nth term is always 3 times our n minus 1 term. Now let's talk about the explicit formula. Remember, explicit formulas don't include previous terms generally. They include the n value, or the position of our term. The explicit formula for a geometric sequence is that the nth term is always the first term times our common ratio again, which is r, but this common ratio is put to an exponent, or has an exponent of n minus 1. This geometric sequence that we're given, 3, 9, 27, and 81, we know the common ratio is 3. Our first term, or a1, that's also 3, because our first term is 3. So we can write the explicit formula for this geometric sequence as an is equal to our first term, 3, times our common ratio, which is 3, to the n minus 1 power. So if that's our explicit formula, we can test this out. If we wanted to find the fourth term in our sequence, which we know is 81, that would be A4 is equal to 3 times our common ratio, which again is 3, to the n minus 1 power. Well, we're looking for our fourth term, so n is 4, so this would be to the 4 minus 1 power. So our fourth term then is just 3 times 3 cubed. Now 3 cubed is 27. And 27 times 3 is indeed 81. So our fourth term then would be 81, which we know it is. So that's how you can write recursive or explicit formulas for a given geometric sequence. Now the last thing we have to talk about is the geometric mean. The reason why we have a geometric mean is for geometric series or sequences. If we need to find a missing term in a geometric sequence, we can typically use the geometric mean. Now you may know about the arithmetic mean, but arithmetic means don't work for geometric sequences, and let's see why. If we call the x-axis here the n-axis, or the position of our sequence, and then the y-axis is the value of our terms, so the nth term axis, then we can plot our sequence 3, 9, 27, and 81. Our first term is 3, and that would be roughly right about there. Our second term is 9, and that one would be roughly there. Our third term is 27, that would be about there. And our fourth term is 81, and that would be way up here. Notice that these terms are following the shape of an exponential graph. Now let's say we didn't know our third term, and we wanted to find this third term. All we knew is 3, 9, some term, and 81. Well, if we tried to use an arithmetic mean to find this term on a geometric sequence, between 81 and 9, we would find that our value would be, roughly here. And this is about 41, 42. But since this is a geometric sequence, that would be incorrect. So instead, to find our missing term on a geometric sequence, we use what's called a geometric mean. And the geometric mean is kind of like an arithmetic mean. Instead, we take our two terms that are on either side of that missing term, so in this case 9 and 81, and we multiply those numbers together. If we multiply 9 and 81, we would get 729. Then we take the square root of that multiplication, so the square root of 729. And if you take the square root of 729, you'll get 27, which is what we were hoping to find. So if you have a geometric sequence and you're missing a term, you have to use the geometric mean to find that term. So let's practice this again. Here we have 24, a missing term, and 96. Well, the geometric mean tells us that if we want to find this term, we take the terms that are on both sides of it, 24 and 96, and we multiply them together, and then we take the square root of that multiplication. Now 24 times 96 is 2,304. If you take the square root of 2,304, you'll get 48. So our sequence then would be 24, 48, and 96. So that's how you can use the geometric mean to find missing terms in a geometric sequence. If it's a geometric sequence, then each term is multiplied by the same number to get the next term in the sequence. So looking at our example sequence here, 1, 3, 9, 27, and 81, my first term is 1. And to get my second term, I would take my first term, 1, and multiply it by 3. Now if I wanted to find my third term, I would take my second term, 3, and I would multiply that one by 3, and I would get my third term, 9. To go from 9 to 27, I would take 9, and I would multiply that one by 3. And to go from 27 to 81, again, I would multiply my fourth term, 27, by 3 to get my fifth term, 81. If these multiples between each term is the same, in this case 3, then this is a geometric sequence. Now if you take all these same terms and you add them together, then you take your geometric sequence and you make it a geometric series. A geometric series is just a geometric sequence where all the terms are added together. Now there are two different types of geometric series. There are finite and infinite geometric series. First, let's look at sequences. If we have a finite sequence, like the one in this example, 1, 3, 9, 27, and 81, notice that 81 is the last term in our sequence. So the sequence ends at 81. If we have an infinite sequence, like this example 1, 2, 4, 8, 16, notice that there are these 3 periods after our last term. That means that this sequence goes on forever. The pattern between 1 and 2 we would multiply by 2. Between 2 and 4 we would multiply by 2. Between 4 and 8 we would multiply by 2. Between 8 and 16 we would multiply by 2. And then these 3 periods here means that there's another term after 16, and that would be 32. Then there's another term after 32, that would be 64, and so on until we hit infinity. Now if we have a finite series, then we're taking a finite sequence and we're adding all the terms together. If we have an infinite series, then we have an infinite sequence and we're adding all of those terms together, but we'd always be adding another term forever. So we have 1 plus 2 plus 4 plus 8 plus 16, and notice there's these 3 periods at the end here. That means we're adding 32, and then we're going to add 64. And we're going to continually add numbers until we're adding infinity. So the difference between a finite and an infinite series is that a finite series has a final term that's being added. An infinite series always has another term forever continually added to the end of this series. Now if we have a finite geometric series, that means that there's a final term at the end of our series, and we can find the sum or evaluate this series for its sum by adding all the terms together. So if I have 1 plus 3 plus 9 plus 27 plus 81, I can take 1 and 3 and add them together and get 4, then add 9 and get 13, then add 27 and get 40, and then add 81 and get 121. But imagine if this series had a lot more terms. Say this series had 35 terms on it. Then you probably wouldn't want to add each term individually. Instead, you can use this formula right here to find the sum of a finite geometric series. This formula means S of n is just your sum, where n is the number of terms in your series. In this example here, there's 5 terms, 1, 3, 9, 27, and 81. A1 is the first term in your series. In this example, that would be 1. N, again, is the number of terms in your series, and R is your common ratio. Your common ratio is the number that each term is being multiplied by. So if we took this series, 1, 3, 9, 27, 81, and brought it back into a sequence of 1, 3, 9, 27, and 81. Well, to go from 1 to 3, we would take 1 and we would multiply it by 3. To go from 3 to 9, we would multiply it by 3. From 9 to 27, we would multiply by 3. And from 27 to 81, we would multiply by 3. this 3 that we're multiplying by each time to find the next term is r. This is our common ratio. And that's what would get plugged in to this formula here in both locations for r. So if we wanted to use this formula to find the sum of this example series here, well then our sum, and you can put the n at the bottom here, there's 5, so the sum of these 5 terms is equal to the value of our first term, a1, which is just 1, times 1 minus r, which is 3, our common ratio, to the n power, so the 5th power, because there's 5 terms. And then this is all over 1 minus our common ratio of 3. Now to further simplify this, 3 to the 5th power is 243. Now we're multiplying by 1 out here in front, and anything you multiply by 1 is just itself. So this will simplify into 1 minus 243 divided by, now 1 minus 3 would be negative 2. 1 minus 243 would be a negative 242 over negative 2. So the sum of these 5 terms is 121, which is exactly what we got before. So that's how you can use this formula to find the sum of a finite geometric series. Now sometimes you'll see a geometric series written in summation notation. Summation notation is indicated by this crazy E here. This is the summation sign. Above the summation sign is what's called the upper limit. This typically, when we're talking about geometric series, is the number of terms that we're going to be adding together. Or sometimes you can think of this as the maximum value of n. The lower limit, or the number that appears underneath our summation, usually when you talk about geometric series, this is 1, or you'll see it is listed as n is equal to 1. This is the beginning value of our summation. Now next to the summation sign, you'll see the explicit formula for this geometric sequence that makes up our geometric series. So if we went back to our example series of 1, 3, 9, 27, and 81, we would have to write the explicit formula for the sequence of numbers that are 1, 3, 9, 27, and 81. Now the jump between each of these terms is 3. So our common ratio, r, is 3. Now the standard explicit form of our formula for a geometric sequence is that every term in our sequence, or the nth term in our sequence, is equal to the first term in our sequence, so a1, times our common ratio r to the n minus 1 power. Now in this sequence, our first term is 1. Our common ratio is 3. So for this sequence, our explicit formula would be 1 times 3 to the n minus 1. Now, we don't plug in anything for n because as we move along to different terms in our sequence, the only thing that's changing in this formula is our value of n. If I simplify this, my explicit formula is an is equal to, now 1 times anything is just itself, so 3 to the n minus 1 power. This explicit formula is what goes here at the end of our summation. So the summation of this example series would look like the summation. My upper limit is the maximum value of n, which in this case there's 5 terms, so this would be 5. We're going to start with the first term when n is equal to 1. And then at the end here, we have our formula, 3 to the n minus 1 power. So this would be the geometric series 1, 3, 9, 27, 81 written in summation notation. So here we're given a geometric series written in summation notation. So how do we evaluate this? Well, if we have the summation of 5 times 2 to the n minus 1, when n is 1 to 5, then we would just plug in all the integer values for n between 1 and 5. So this is equal to 5 times 2 to the 1 minus 1 power plus 5 times 2 to the 2 minus 1 power, because I move from 1 to 2 in my value of n, plus 5 times 2 to the 3 minus 1 power, plus 5 times 2 to the 4 minus 1 power, plus 5 times 2 to the 5 minus 1 power. And I stop there because 5 is my maximum value of n, or my upper limit. Now, 5 times 2 to the 1 minus 1 power. Well, 1 minus 1 is 0. 2 to the 0 power is just 1. And 5 times 1 is just 5. So we add that to 2 to the 2 minus 1 power. 2 minus 1 is 1. 2 to the first power is just 2. And 2 times 5 is 10. We're going to add that to our third term, which is 5 times 2 to the 3 minus 1 power. 3 minus 1 is 2, so 2 to the second power is 2 squared, which is 4. 4 times 5 is 20. And we're going to add that to our fourth term. 5 times 2 to the 4 minus 1 power. 4 minus 1 is 3. 2 to the third power is 8. 8 times 5 is 40. And we're going to add that to our fifth term. 5 times 2 to the 5 minus 1 power. 5 minus 1 is 4. 2 to the fourth power would be 16. 16 times 5 is 80. So those are all 5 of my terms. 5 plus 10 is 15, plus 20 is 35, plus 40 is 75. 75 plus 80 is 155. And that would be your solution. So that's how you evaluate a finite geometric series that's written in summation notation. Now we've talked about trying to find the summation or evaluating finite geometric series. So now let's talk about trying to find the summation or evaluating infinite geometric series. And when we try to find a value for an infinite geometric series, we talk about convergence and divergence. Now to find out whether or not we can find a sum or a value for an infinite geometric series, that all depends on whether it converges or diverges. And if it converges to an answer or it approaches a single number, then we say it's converging. If it does not approach a single number, then we say it's diverging. To determine whether it converges or diverges, the key is to look at your common ratio, r. If your common ratio r is less than 1, then your geometric infinite series does have an answer. If the absolute value of your common ratio is greater than 1, then your infinite geometric series does not have an answer. Now let's look at why this is. If our r value, or the absolute value of r value, is less than 1, some fraction, then we should be able to get an answer from our infinite geometric series. So here we're told that r is equal to 1/2, and our first term in our sequence is 1. Now remember, this goes on for infinity, so we start with 1, but our next term is just 1 times our common ratio, so our next term would be 1/2. The next term after that would be our second term multiplied by our common ratio, so that would be 1/4. After that, we would be adding 1/8. After that, we would add 1/16. After that, we would add 1/32. And again, 1/64. After that, 1/28. And so on and so forth. But notice what's going on here. We're continually adding a smaller number. Again and again, each number that we add on is smaller than the one before it. So each additional number that we're adding makes a smaller impact on the total sum of all these numbers. If I add 1 to 1/2, I get 1.5. Add 1/4 and I'm at 1 3/4 or 1.75. Add an eighth and I'll be at 1.875 or 1 7/8. Add a 16th and I'll be at 1 15/16. Add a 32nd and I'll be at 1 31/32. Add a 64th and I'll be at 1 63/64. If I add 1/28, I'll be at 1 127/128. Now I'm continually adding a smaller and smaller fraction, and I'm getting closer and closer to the value of 2. Now I'll never actually hit 2, but we can say as we continue to add smaller and smaller fractions, we're getting closer and closer and closer to 2. So we would say that this infinite series converges on the number 2. Now let's look what happens when our r value is greater than 1. This is when our infinite series diverges. Here I have an r value of 2 and my initial term is 1. Well, if my r value is 2 and my first term is 1, then my second term would be 2. My third term would be 4. My fourth term would be 8. The term after that would be 16, and then 32, and then 64, and I'm adding all these numbers together. So each time I'm adding a larger number. So this is just going to get bigger and bigger and bigger, or it's going to go to infinity as I continually add more terms. So that is why if your r value, or the absolute value of your r value, is greater than 1, then there is no answer to your infinite geometric series. If the absolute value of your r is less than 1, then your series will converge at an answer. Now say we know that our infinite series does have an absolute value of r is less than 1, which means this is going to converge at an answer. If we wanted to find that sum, then we could use this formula. The sum is equal to our first term divided by 1 minus our common ratio. So that's an easy formula. Let's try using it. Here we're given two infinite series. We can tell that they're infinite series because our upper bound here is infinity, which means our n value will always increase forever. To the right of our summation sign here, we have our sequence formula in standard form. And remember, that looks like an is equal to a1 times r to the n minus 1. In our first example here, our r value is 1/5. This absolute value is definitely less than 1. So we can find the value that this series converges at. We just use our formula S, or Sn, is equal to our first term, a1 over 1 minus r. Our first term, that's when n is equal to 1. If I plugged in 1 here, I'd have 1 minus 1 in the exponent. 1 minus 1 is 0. So I have 1/5 to the 0 power, and anything to the 0 power is just 1. So this whole term here is equal to 1. And 1 times 2 is 2. So my first term here is 2. Take 2 and divide it by 1 minus our common ratio, which is 1/5. And this becomes 2 over 4/5, or 10/4. So this infinite series will converge to the sum of 10/4, or you can think of that as 5/2. Now let's look at our next example. Here we have 3 times 3/2 to the n minus 1. This means that our r value here is 3/2. Well, 3/2, or the absolute value of 3/2, that's greater than 1. So this infinite series does not converge. This is divergent. So we would say that this infinite series diverges. Or you could say that it has no solution. So now that we've covered convergence and divergence, that completes the tutorial on geometric series.